I'm going to actually absorb them into the next unit of material. So some of this is stuff we're just kind of hitting for a second time. Remember we said that there is an upper limit and a lower limit with regard to the mass of a star. And I know you're going to see 300 solar masses, but I still want you to think 100 times the mass of our sun as the upper limit for the mass of a star. Remember, a lot of stars can be born at the same time, all in that stellar nursery, all in that one big, what we call giant molecular cloud. And the problem with something that's too large is its fusion rate is too crazy fast. And so basically, since its fusion rate is too high, it can't settle down, okay? So these couple slides kind of talk about that. This says that anomalously, they have found stars that are larger than 100 solar masses out there, but they are exceptions, up to 300 solar masses. Okay. And this is a picture of a star trying to kind of settle down. So the lower limit of a star, and this is something that's important to talking about stars in general, so it might make it to your test, is actually 0.08 times the mass of our sun. Okay? And so these slides kind of talk about why, if something's too light, why doesn't it go ahead and turn into a star? Well, one of the things about turning into a star is it needs to have nuclear fusion going on in its core, just like our sun does. Okay? And if it's too light, it'll never create the temperature and the pressure needed to do that. So in the video we watched, the part of the video we watched on Monday, they talked about this degeneracy pressure. And so there are kind of an assortment of degeneracy sort of pressures. But degeneracy pressure simply means that something that, think of it this way, and they kind of in the video talked about a climber falling down and kind of being stopped. Degeneracy pressure stops kind of the collapse. So one way to think of it is, in general, we have a degeneracy. It's not collapsing, but matter from this hand cannot go through matter from this hand. Okay, I clap them together and they don't just like go like that, okay? Basically, and it's electrons in the atoms of this hand and electrons in the atom of this hand will not allow this to happen. These are solids, okay? So we talk about electron degeneracy as basically kind of stopping matter from moving into other matter space. There's another sort of pressure called thermal pressure, and I like this video because basically what it does is have a balloon that's cold, a balloon that has a certain amount of gas particles that's cold, and a balloon that has a certain amount of gas particles, the same gas particles that are hot. And one of the things we talked about in here is that when matter is cold, it doesn't go very fast. Okay, it has not very much motion. When those gas particles are warm, they have a lot of motion. Okay, so we have this kind of thermal pressure going on. But degeneracy pressure can be thought of as, remember I said that the atoms won't share the same space? Okay, degeneracy pressure can kind of be thought of as playing musical chairs in a sense. Okay, so here we have a room with lots of chairs, lots of different places to sit, and we can kind of think of those people as atoms that need to sit somewhere. All sorts of options. Okay, in the second scenario, we've removed some of those chairs, so there's a limited number of places to sit. And degeneracy pressure says, thou shalt not sit on thy neighbor. Okay? So basically, we've switched them down to the point of they cannot occupy the same chair. Okay, musical chairs. Which I always like dread that when the music stops, you're like, oh, can I find a chair? Right? Okay. So, objects that are like objects, and you're going to hear me call brown dwarfs failed stars. And hopefully you'll kind of see how that is. In fact, I think the video even talks about them as failed stars. But a brown dwarf is an object that is less than 0.08 solar masses, and it tried to become a star. Okay? But basically, it got nice and toasty and things like that. But its mass said the atoms that were part of that star that wanted to be that brown dwarf said, I'm not moving anymore. Degeneracy pressure. It stopped contracting. It stopped contracting, and in the core, it wasn't hot enough, nor did it have sufficient pressure to go ahead and start beginning nuclear fusion. It couldn't become a main sequence star. So brown dwarfs, gotta love them. In fact, brown dwarfs will glow for a while, and that's why you can see that we find brown dwarfs by kind of tuning our telescope to heat, thermal energy, infrared radiation. The exotic thought of dark matter, like, ooh, dark matter, what is it? Well, honestly, some of it is dark, it's just regular matter, it's just we can't see it. So underluminous matter, like brown dwarfs, that counts as dark matter. All right, so to kind of summarize, and I know this says 300 solar masses, but I think for purposes of your test and the way I learned it, I would go with 100 solar masses. Okay, so you're going to want to be able to, and if you come to the review session, you're going to hear me say this again. Not only do you need to kind of be able to tag the upper end mass of a star and the lower end mass of the star, but for 3 points, you need to be able to kind of describe why is there an upper end and why is there a lower end. Okay. So actually, here is something we talked about in our last chapter. We said the first stage of a star, when a star is finally began thermonuclear fusion in its core, it arrives at the stage we call main sequence. So all of these stars, these beautiful large blue ones and these cute little red ones, okay, are fusing hydrogen in their core. Okay. And not only that, but, and this is kind of reviewing a little bit, but we said that these are large mass, okay, and these are low mass or small mass, as they are main sequence stars. Okay. So, I'm going to kind of revisit this in a minute and kind of tack on something that's low mass. But for purposes of kind of drawing a line in the sand and saying these low mass stars do this thing and these high mass stars do this thing, we're going to kind of set that line at 8 solar masses. So anything that's lighter than 8 solar masses, that would include the sun, right? Because that's 1 solar mass. 8 solar masses or less, we're going to call them for now low mass stars. Okay? And they do a certain thing, and that's what we're going to talk about now. And actually, that thing that they do, I know it's kind of small, is actually all kind of summarized on this one little figure. Okay, this is something we talked about. Remember the protostar, kind of the jets of energy, and the accretion disk that may or may not form planets. This one, if you look at it closely, it's going to say main sequence. One of the things I don't like about this figure is, and I hope you can appreciate this, is the main sequence stage takes a long time. Okay, relative to those other things, these are fast. Okay, long time the star being a main sequence star. Okay, then these are giants. And this is a planetary nebula, which are lovely to look at through the telescope. And this is a white dwarf. So in a nutshell, anything that is less than 8 solar masses, this is kind of how it's going to live its life. Okay. So again, thinking ahead to the test you're going to take on Friday, I have a few places where I ask you I'm trying to make sure we all are on the same page. That if a star is a main sequence star, if it's in its main sequence stage, it is, like our sun, in its core, fusing hydrogen to form helium. Okay. But we need to kind of talk about what happens after the hydrogen runs out. And the video kind of addressed this. Okay. So here we kind of see the yellow arrows saying something is departing the main sequence. Now, if something is moving on the HR diagram, then it must be moving with regard to luminosity and temperature. Okay, it's changing. It's changing its luminosity and temperature. And I think we talked about this before. We said that giants in general have high luminosity, high L for luminosity, and they have low temperatures. I know they have low temperatures because they're over here. Okay, so we're going to take a look at what's happening internally after a star basically is no longer a main sequence star and ran out of hydrogen. And again, we're kind of talking about 8 solar masses. Actually, as we talk about something that's more massive than 8 solar masses, it's going to have kind of a similar end. So, here we have a main sequence star, okay? There in the center, we have hydrogen going to form helium, okay? So, when it runs out of hydrogen in that cute little red orb core, basically what hydrogen did, let's put it this way, when it runs out of hydrogen, its fusion rate slows down, okay? So instead of having this amount of pressure going out, it has this amount of pressure going out. And remember we said what's coming in? Gravity. So that's why what this says is when hydrogen starts to run out, and I think it's about like 10% hydrogen left, not converted to helium, then the thing starts to, gravity starts to win out, and it no longer stays the same size. But what's weird is basically it contracts near its core, but it swells near its surface. That's the whole giant thing. Okay. So it's running low on hydrogen. It's no longer at equilibrium. It starts to contract. One of the first things that happens is it has fresh hydrogen. I don't know if you can see this purple. The purple represents the helium, okay? And this right here, this kind of red around there, is a shell region around the spent hydrogen. It's fresh hydrogen, and now because of contraction, that region outside the core is hot enough and has sufficient pressure to go ahead and begin hydrogen fusion. It's called shell hydrogen fusion. Okay. So it moves on the HR diagram. It leaves that diagonal it's been on like forever, okay, and it goes up to the giant region. The giant region, again, if it goes up on the HR diagram, it's increasing luminosity. If it goes over this way a little bit, it's lower surface temperature. So what eventually happens, though, is that purple, it was purple here, it is basically that helium that was built up from hydrogen fusion. Eventually, contraction will create the temperature and pressure needed for that purple to go ahead and do this. Okay, what is this? This is helium fusing to form carbon. And I think on the video we watched Monday, it talked about throws the star a lifeline. Okay? So actually, for a while, it's going to kind of develop a new sort of equilibrium, but it's not going to last very long. Okay. So this talks about a helium flash. I wouldn't worry too much about this, but it kind of makes sense. It just says that sometimes this new sort of core fusion can happen abruptly, and it's kind of like a burp. So I like this slide because it kind of puts a little bit of scale to it. So I know I said purple before, but it kind of looks like purple-pink. Okay, so right there is the helium. Now we have, if it's going ahead and fusing to form carbon, that's cool. But the outside is swollen and the inside is contracted. Again, these are like what we call the giants, kind of the upper, kind of north of the main sequence. So this is kind of in a nutshell those low mass stars. Okay, remember we talked about after the main sequence, it goes up here, becomes a giant. And actually, can you kind of see the wiggle? And I'll kind of emphasize this just a little bit. It leaves here and goes here, up here, down here, up here. Okay, that's kind of the wiggle, and actually I have a name for that. It's called the horizontal branch. Okay, it's a little bit of wiggling up there. It's no longer main sequence, it's kind of on its way out. Finally, when it's really on its way out, it does this and all the way down to this. So here is that horizontal branch I was talking about. Okay, those would be stars that are they've left the main sequence they can kind of go through an assortment of little mini stages, okay, all on their way out the door, basically. Notice that actually one of the things we talked about in, and I think I'm going to maybe say it again, but we said that if all of these stars were born about the same time, we can throw them up on an HR diagram and look for basically where the high mass stars have left the main sequence. That's called the turn-off point. So scientists love, and you can't blame them for loving this, but they love it when they come up with, in theory, like paper and pencil, how things should work, okay? And then they compare that to the true situation, like applied science, okay? And so actually going back and forth, the physics of a star makes sense with what they're seeing. I don't know if that's kind of what I wanted to say. All right. Oops. Did you need anything there? I guess not. Okay. So I told you about shell fusion. I said that actually if it's a solid helium core, that star is going to contract, and we can go ahead now outside that helium core where there's fresh hydrogen, and we can get the pressure and the temperature needed to fuse outside the core hydrogen. That's called shell fusion. But actually, there can be multiple shell fusions. So here in this lecture in a little bit, you're going to see that onion kind of structure that we saw in the video on Monday. Okay, what I mean by an onion sort of thing with regard to a star is you see the core of the star, then you see these assortments of shell fusions. And always, if you look at a picture of a star like that, in its core is going to be the heaviest elements that are fusing, and then right outside that, a little less heavier element, less heavier element, less heavier element, less heavier element. Okay, more and more complicated shell fusions. And this kind of actually, one way to think of it, on the previous slide, the shell fusions, this kind of takes it through that horizontal branch, sort of wiggling amongst the giants, okay, stars. Remember that a star is not a giant near as long as a star was a main sequence star. So this is an example of the planetary nebula. Now remember way back in Unit 1 we talked about a nebula, and all a nebula is basically in outer space there's a cloud. Okay, and it's not a cloud of water necessarily, but it's a cloud of stuff that may or may not form a star. It's a cloud of stuff that maybe came from a star. Okay, so it's a nebula. These are called planetary nebula because I think that they were one time mistaken for planets. Okay, and nebula, planetary nebula, or other sort of gases nebula up there, they're given proper names. Like this one, I think might be called the Helix Nebula. Yeah, it says underneath there. Okay, so there's only one Helix Nebula. So I'm going to kind of, I mentioned that because it took me a while. I'm like, okay, so where's my next Helix Nebula? And that's its proper name. There is a ring nebula in Lyra. That's kind of beautiful. There's a dumbbell nebula. Okay, so the ring nebula looks like a ring. The dumbbell nebula looks like a dumbbell. Okay, so these are planetary nebula. And like you saw, or like in the context of this discussion, these are basically after the star is kind of done its giant stage even, and it's on its way to become a white dwarf. This is kind of the ejected outside of the star. It's just beautiful. Okay, so here's another planetary nebula. The Butterfly Nebula, I buy that. Sometimes I look at things and I'm like, really? How did you come up with that name? Okay, that is very beautiful. Now eventually these things will stop glowing, okay, and just kind of turn into darkness. Okay, another. So kind of after the nebula stage, okay, it's done fusing, okay, and basically it has a kind of a pretty dense object. And I know that video we watched Monday talked about how compact that orb that used to be a star, how compact it is. And it makes sense that it's compact because for a long time it had gravity doing its thing, okay, and of course fusion in the core doing its thing. Okay, and eventually gravity just won out because it's done doing fusion because it ran out of fuel. So the thing that's left and going to become just cool off okay, is called a white dwarf. Now, eventually the white dwarf will cool off into becoming a brick, okay, a piece of charcoal. In fact, white dwarfs, I think in the news, this has been a year and a half ago or so, I heard scientists talk about, because there's a bunch of carbon in a white dwarf, okay, because basically helium was fused to form carbon. So these white dwarfs, these retired stars, they could be a big old diamond. It's kind of interesting. Okay, so white dwarfs are very compact. So the discussion we've had just now about kind of the whole main sequence, giant, kind of the horizontal branch, sort of kind of back and forth, going over to a planetary nebula, cooling off to a white dwarf. That's what our sun's going to do. And sometimes students or little kids will ask, well, when it's a giant, how big is it? And I can't remember. I'm pretty sure it's at least out to the orbit of Mars. Okay? So you're like, oh, we better relocate. Okay, but we got 5 billion years to kind of work on that. So just to kind of summarize again, after main sequence, we've got this sort of deal up here. Notice that at this point, the star is still alive. It's kind of on its last gasps. It has shell hydrogen and shell helium fusion. Okay. And it's kind of, and I won't, this semester I'm not necessarily going to kind of test you on the subtle differences in the giant region. What I want you to know is once it's left the main sequence stage, if you're looking at its core, it's no longer fusing hydrogen in its core. It's probably the biggest thing. All right, so I told you a low mass star is 8 solar masses. Well, I want to tell you, add on one more little tidbit. A low mass star has a kind of a different end to it, and that whole scenario is right here on this slide. So this actually, when a low mass star then would be, like this slide says, less than 0.4 solar masses. Put another way, what we talked about that happens to our sun goes from 8 solar masses to 0.4, and then from 0.4 to 0.08, this is what happens. And this is kind of a beautiful thing, because actually those low mass stars, main sequence stars, do you remember these cute little red ones down here? We called these red dwarfs. I think we called those the red dwarfs the other day. Red dwarf main sequence stars. Well, red dwarf main sequence stars, this is what they do. They're so light and cute, okay? What happens is, we've talked about convection a lot in here. All convection means is basically you have a blob that's warm, and it's going to rise up, it's going to cool down, it's going to sink, and it's going to get warm, and it's going to rise, okay, and it's going to cool down, it's going to sink. So these actually are convection cells, but what they're dredging up is basically helium, which is formed from hydrogen fusion, out of the core, and fresh hydrogen into the core. So they're so chillaxed that basically they can have these little convection cells kind of dredge in new hydrogen, dredge out the spent helium, okay? So the thing will not go ahead and do the route that we were just talking about. Honestly, these things will just kind of end their lives. They will never, put another way, fuse helium to form carbon. They'll just end up as an orb of helium. All right. High mass stars, and I don't have I guess in the next chapter I will, because there's kind of two, there's a high mass and there's a high mass, right? But high mass are just more massive than 8 solar masses. And the difference here is, I'll just kind of highlight it. Okay, similarities are good. This is all similar. What's different are these two things. Basically, a high mass star is going to end its life in a supernova event, and then this thing that's left over is not going to be a white dwarf. Instead, it's going to be one of two things. It's either going to be a neutron star, and I know the video we watched talked about that, or the other option is a black hole. So stars that are more massive than 8 solar masses, one of the things they can do is give us this stellar black hole. Now there's all sorts of different ways to create a black hole. This is one of them. Okay. So at the risk of you not just totally blowing off this slide or anything, I'm not necessarily going to test you over this, but the C, N, and O stand for carbon, nitrogen, and oxygen. And again, we're talking about more massive stars, and this is kind of talking about how those massive stars can do this additional fusion. Okay, remember though, massive stars, they burn through their fuel faster. Okay. They have a few more options. So this slide kind of emphasizes what is the same about high mass stars from low mass stars. What's the same? Well, they start out as main sequence stars, fusing hydrogen in their core. They will do that whole shell hydrogen fusion when they start to collapse and they have helium in their core. And they will fuse helium to form carbon as kind of their second stage. Okay, but they will do more than that. So this actually is the different elements that we have here in the universe. Isn't that awesome? So remember the way it works is that you kind of see that, for instance, if we pick on potassium, K, the whole number for potassium is 19. Okay, and then we have calcium, which is 20. And remember what those numbers are the number of protons in the center of those atoms. So we basically kind of fill in the blank with regard to the possibilities of having different numbers of protons. Okay, numbers of protons in the atoms of these different elements. So as this turns out, notice then, as we go from left to right, we're increasing the number of protons. And also, we take a big step as we go down what we call the period. Okay, so for instance, francium has 87 protons. So just to kind of glance at how we get those different elements from stars. Well, we can get straight off the bat carbon, nitrogen, and oxygen from stars. Just regular fusion. Okay, and this kind of talks about how other fusion can occur. Okay, again, this is massive stars. The little superscript, like C with the 12 protons. Oxygen with 16 protons. Neon, 20 protons. So if you want one of those atoms, you got to do nuclear fusion. Who can do that? Stars. Okay, so kind of emphasizing where neon, magnesium are. And I have a slide coming up, but it's kind of cool, and it goes back to this helium capture that you saw, but we kind of end up with every element, like we skip an element with regard to abundances. Okay. Oh, I told you wrong. That number up there, 12, darn it. That number up there is its mass number. Sorry. Carbon has 6 protons. Oxygen has 8. Silicon, I'd have to look. Iron has 26 protons in their nuclei. So, did you hear how Alec Filipenko, I think is his name, on the video we watched Monday, he got so excited about iron. Okay, we're coming up to that point. Okay, so the thing here is that actually stars can do this in their cores up to iron. Okay, and then something else has to create anything above iron, which is a lot. If you find iron on the periodic table, right between manganese and cobalt, everything heavier than iron had to be produced from something other than this. Okay. So here's just the handful of elements that was on the previous slide. So here's the whole onion thing. Again, you'll only see a complicated onion with massive stars. And if you look closely at what that onion is, it's like I was telling you, basically the heaviest and most complicated atoms are at the center, and it gets lighter and lighter and lighter and lighter. And actually, those are forms of shell fusion, and the the outside shell fusion is called the hydrogen shell fusion. Okay, so this actually is, and we'll be talking more about the death of a massive star, the whole supernova blow-up thing, 8 solar masses or larger. But this is right before it blows up. I know this because its core is iron. Okay, and like Alex said, you cannot take iron atoms and fuse them together under high pressure and temperature. You can, but instead of releasing energy, it requires energy. So it's problematic. So this is actually talking about the amount of energy that can be released, okay, by nuclear fusion or released by nuclear fission, okay. One of the things we talked about before is nuclear fusion is this, stars do this, okay. Nuclear fusion. Nuclear fission is where you take a big old honking uranium atom and you split it, fission. Okay, and in splitting it, you release a lot of energy. So the thing is if you take atoms that are more heavy than iron, actually you'll get energy if you break them apart. So this is kind of the every other sort of looking at relative abundances in the universe, I guess. So it just kind of supports the mechanism of helium capture. All right. So again, we're going to be talking more about supernova blow-ups. We're going to talk more about that, the deaths of stars, in the next unit of material. But this is kind of the onion we have going on in the core area of the giant right before it blows. To get the inner iron core, what last was fused was silicon. So silicon can fuse to form iron, and iron cannot fuse. So one of the things I don't emphasize here, but the video did, was he was like, okay, so I look at a periodic table and I'm like, okay, stars, you haven't given me everything that there is in the universe. Okay, and the other elements are formed as part of the blow-up process, and it's called nuclear synthesis. Basically, on the way out, basically, the guts of the star tumble over each other, trying to escape, literally leave the room, and so they run into each other, and actually that's where we can get nuclear fusion to create these heavier elements. It is amazing. So, but what you will need to know for the test, and actually in the next unit of material, is that little thing that's left over, okay? It's like, blows up, you're like, well, wait a minute, there was something left over. And that thing that's left over will either be a neutron star or a black hole. And one of the things I'm going to emphasize in the next unit of material is we said a white dwarf was dense. White dwarf is very dense, okay, because gravity's like beat on it all its life. Okay, white dwarf, retired star. A neutron star is even more dense than a white dwarf. And a black hole, even more dense. Okay, so that's kind of how that goes. All right. So a lot of times, celestial objects like this are named, in their name is the year that they were observed. So back in the year 1054, okay, there is historic data that a star blew up and has created this remnant, okay, that's been around ever since 1054. This is actually object M1. Okay, so I suppose. Okay, M1. It actually is a supernova remnant. Okay, and it's kind of interesting to, I haven't done it, but I think in your book it talks about how do we know that in 1054 AD they saw this, and somebody wrote it down. And so it's basically this bright object in the sky. Anytime a star blows up like this, it'll stay bright for a couple weeks and then it will decay. So, supernova remnant, that is, you figure all sorts of cool chemistry, all sorts of cool heavy atoms left in that remnant. All right. So 1987 occurred in 1987. So do you remember the guy in the video Monday talked about trying to find, he was talking about the supernova type 1A. These are supernova type 2. We'll talk about the differentiation. But he said to find supernova, he basically would scan galaxies and look for galaxies that had kind of a bright spot. Okay. Well, if you were to scan, look at this star now, and look at this star now. Okay. So if you read the history behind this supernova event, scientists were really excited because they actually, all the stars that they can kind of study and understand, they really studied and understood this star. Okay, so they were really excited when it went because they had that kind of baseline on it. Okay, so that's a supernova. Okay. So to kind of summarize, and actually this brings in the previous chapter, now this chapter, we talked about high mass stars last chapter, how they live their lives quickly. Okay, and they eventually have iron in their core, but iron can't fuse. And so high mass stars, I'll put out the margin there, we're talking about something more massive than 8 solar masses is going to end as, going to blow up. Okay. So high mass, anything that is more massive than 8 solar masses. Low mass stars, and I'll go ahead and put my other, they must be, let's see, how do I say this? They are going to be greater than 0.4 solar masses, okay, but they are going to be less than 8 solar masses in general. So we can get kind of our little red dwarfs. But they eventually, their little cores will become carbon, and the carbon won't fuse. So actually, as they become retired white dwarfs, they're kind of an orb of carbon. That's where I think we should visit. Although, did you hear that the Rosetta, let's see if I got this right. So Rosetta is a spacecraft. The European Space Agency has embarked on this, gosh, is it 10 years? I'm not sure. But this spacecraft has caught up with a comet, and the comet is actually on its way to fizz. The comet is on its way to go around the sun, so it wasn't fizzing. And so it's in orbit around this comet as this comet comes closer to the sun. And so this comet has started to kind of ooze, you know how comets do when they get close to the sun, right? And recently they said that this comet stinks. And so basically this spacecraft is so equipped with monitoring devices, it can detect ammonia, like cat pee, okay, and I think hydrogen sulfide, if that's right. Okay, so basically it's starting to ooze chemicals. It's a comet oozing chemicals. Like, how cool is that? So I just kind of have a few slides to kind of summarize. And remember the last couple of slides on binary stars, I'm going to wait for the next chapter. But we said that a low mass star, and I went ahead and said, all right, even the 0.4 solar masses to 0.08, okay, they, anytime you say low mass in this class, it is going to enter a giant stage, okay? It's going to have shell fusion, and it's going to, when it's done in the horizontal branch or done kind of wiggling around there in the giant region, it's going to become a planetary nebula and ultimately a white dwarf, okay? So there you go. If you're a visual person, put it under your pillow. And then we said, and actually I think I missed, this is the wrong, just ignore this, okay? But this kind of talked about, well, why does it leave the main sequence? Why does it wiggle around, become a giant? These are things we talked about, the kind of more subtle things. A high mass star, we said, is going to do some things very similar to a low mass star. But in the end, we said that it's actually going to be more of an onion than kind of a simple shell fusion. It's going to have more complicated types of fusion in kind of an onion sort of situation. When it has fused silicon to form iron in its core, and it has kind of a core of iron, that iron cannot do any more fusion. We'll talk about the explosion when we come back on Monday after your test. But the thing that I know I tried to emphasize and will be emphasizing in the review session coming up, the thing that's formed in the end will either be a neutron star or a black hole, aside from forming a planetary nebula. So save the last 2 slides until we meet again, no, until Monday. Okay? So got a few minutes to grab a bite if you want, maybe. Remember, you can't eat or drink in the chem lab if you're coming to the review session. But the door's open, and there's a clipboard up there. So feel free to make yourselves at home.